Today we're focusing on Lesson 3, Module 3, Lesson 7 and 8. And our topic is the informal proof of properties of dilations, as well as similarity. So before we start, I have a couple cutouts for you for your notebook. This first one we're going to place at the top, and we're going to use it to look at some angle properties as we discuss some informal proofs of properties of dilations. So what I have in my image is a small angle PQR, and then a slightly larger angle P prime, Q prime, R prime. And what we're saying is that if the angle PQR is dilated to become the angle P prime, Q prime, R prime, what things can we assume? So could Q prime, P prime be parallel to QP? When I look at those two segments of my paper, it certainly looks like those lines are parallel, and it looks like they will not intersect. So I'm going to say they look parallel, which at this point is going to be our best guess. Will Q prime, P prime intersect QR? So again, one of our lines, Q prime, P prime, that's parallel, this is, will it be intersected by QR? And I'm going to say yes, I see an intersection point. And lastly, is Q prime, P prime parallel to QR? Well, if I'm intersecting, then no, they intersect. They're not parallel. What's interesting about these observations is that I have QP being parallel to Q prime, P prime. And when I think about a point on a plane, there's only one line that can go through the point P, the point Q, which will be parallel to the line Q prime, P prime. And we already established that it's QP based on our first question. So QR cannot be parallel to Q prime, P prime. So it must intersect it. Now, the other thing that we can kind of see is if QR intersects both Q prime, P prime, and QP, then it's a transversal to those two sets of parallel lines. So that's great news because that means that we can use our special angles. Remember kind of our alternate interior, alternate exterior, consecutive angles, vertical angles that we talked about early in Module 2. So what I see when I look at this picture are two parallel lines cut by a transversal, and I see that angle PQR is corresponding to angle P prime, Q prime, R prime. So that means they're equal to each other. And if they're equal to each other, then our transformation of a dilation that we conducted conserves angle measure. So moving into Module 3, Lesson 8, which is on similarity, we're going to look at the idea that two shapes can be similar and how to prove that those shapes are similar. So if I have this funky little circle shape, S, and then a smaller version of that shape, S sub 0, we can kind of look and see that sometimes a dilation alone is not enough to prove similarity. So remember, a shape is similar if it's the same shape. It has angle conservation now, but it's not necessarily the same size. Shapes can also be similar but not be in the same position or orientation. So sometimes we need a dilation and a sequence of basic rigid motions like we did in Module 2 to determine whether or not a shape is actually similar and congruent. So I'm going to paste my next example here. And it says, in the picture below, we have a triangle DEF that has been dilated from center O by scale factor R equals 3. It is noted by D prime, E prime, F prime. We also have a triangle D double prime, E double prime, and F double prime, which is congruent to the triangle D prime, E prime, F prime. So, what's important here? How do I know that DEF is similar to D double prime, E double prime, F double prime? Well, first I'm plotting all my coordinates here, and I'm looking and I'm seeing, yes, DEF is a dilation with a scale factor of 3 to D prime, E prime, F prime. So how do I map D prime, E prime, F prime to D double prime, E double prime, F double prime? Now, this is like a question for Module 2, right? I'm looking at this triangle, and I'm saying, what series of basic rigid motions can I use to transform it onto its image? So I cut out this little triangle so I can show you step by step. First, I'm going to translate that point F 6 units to the left. So now I have those points that are lined up. And I'm going to rotate triangle D prime, E prime, F prime about 45 degrees counterclockwise around point F. Remember how specific we have to be about this. The last step is to reflect that triangle over the line segment D prime, F prime. Now that they match up, I know that they're congruent, which means to get from DEF to D double prime, E double prime, F double prime, I had similar triangles.